So our first question is going to be, if we're trying to do optimization, find a maximum and minimum point of a function, figure out how large can the value of a function get and how small can the value of a multivariable function get. The first place to start that process is to look for critical points. And in single variable calculus, when we looked for critical points, we were looking for a place where our single variable function was neither increasing, so going upwards from left to right, or decreasing, going downward from left to right. And so any place where those functions were not increasing and also not decreasing, we called those the critical points. And we ended up being able to use the single function, the single variable function called the derivative, to tell us where a function's increasing and where it's decreasing. And so that function's value can tell us where are the points which are neither increasing nor decreasing, and those are the critical points. And it was a pretty cut and dried question. At a critical point for a single variable function, the value of the derivative is either 0, in most cases, or undefined, right? Those are the only ways to get a critical point for a single variable function. In multivariable calculus, though, we don't have really a notion for whether a function of several variables is increasing or decreasing. We can't really answer that question unless we specify a direction. Is my function increasing in the x direction? Is it increasing in the y direction? Is it increasing in some diagonal direction, which we could measure with a directional derivative? And so already the question gets more complicated. So to get us a good notion for what a multivariable critical point ought to be, we have to take care that we're specifying what direction of increase are we sort of thinking about here. And so directional derivatives come to the table. Let's sort of set the stage for how we want to have this discussion. So if I have a point in the domain of a multivariable function and a direction from that point along which the directional derivative is 0, right? That would mean that a tangent line to my graph in that direction is going to be a horizontal tangent. So this is one such example, right? This tangent line facing in this direction. So at the point 1, 1, facing in the 1, minus 1, the southeasterly direction, that tangent line is horizontal. But there's other tangent lines at that point, like the tangent line facing in the y direction, for example, that doesn't have a slope of 0. And so if we ask a question like, is this function increasing or decreasing in a certain direction? So in some directions, this function is increasing. In other directions, the function is neither increasing nor decreasing. But there are probably also some directions, like this one here, along which the function is decreasing. Right? And so probably we would not want to call this point a critical point of our function of several variables, because it's clear just based on the variety of different directional derivatives, right? Some of them are positive, some of them are negative, and some of them can be 0. Right? But that means that at this point there is a direction in which I can move that will increase the value of my function. And there's also directions I can move that will decrease the value of my function. So probably this point would not be what I would want to call a critical point. Right? We would probably want a critical point to be one in which there is no direction locally along which the function is either increasing or decreasing. Right? We would want for it to be a point at which the slopes of all of our tangent lines are neither positive nor negative. Right? And the most common way in which that would happen is to find a point on the graph of my function where all of my tangent lines are horizontal. And so for this particular function, I think the only place we're going to find such a point is right here at the top of the mountain. Right? So at this point, no matter what directional derivative I take, the directional derivative in that direction is going to end up being 0. So those are going to be the directions that we're going to want to, those are going to be the points that we want to call the critical points of a multivariable function. And so where we want to start our investigation for today is in section 10.7 of our text and the preview activity for 10.7. So just give me a second here. So the preview activity in this section is actually it's actually pretty conceptual, which is different actually than a lot of the preview activities that we end up doing in this text, because what the preview activity is going to ask us to do is to think about at a place where we're going to want a critical point, a place, for example, where a function achieves a local maximum. So the picture that we would have here is a picture that's just like the one that we were looking at here, right? If we're at a place that's a local maximum of a function, what do we think ought to be true about the partial derivatives, and then what do we think ought to be true about the gradient, and then what do we think ought to be true about the tangent plane? And then after answering all of those questions, part E is going to ask you to find any points at which this particular function, f of x and y, is 2x minus x squared minus the quantity y plus 2 squared, might have a local maximum. So I'm going to go ahead and hand over the floor to you all to be talking about and putting your responses to 10.7.1 into your Teams file for today. Great. So in this first preview activity, you decided that in order for us to have a candidate point for a local maximum to a function, we should be at a place where the y partial derivative and the x partial derivative are both equal to 0. Right? Because if either one of those two is non-zero, then that means there's going to be some direction that we can walk that's going to take us uphill. Right? And if there's some direction that we can walk that's uphill, that means we must not yet be at a local maximum. At a local maximum, there should be no direction that points uphill. And the only way for there to be no direction that points uphill is for the x partial derivative to be 0 and the y partial derivative to be 0. And in such a case, that means that every tangent line is going to end up being horizontal. And that's because we know that every directional derivative is going to be the dot product of the gradient vector with the direction that we want to measure the derivative in. Right? And if both the x and the y partial derivatives are equal to 0, that means that the gradient vector at that point is the 0 vector. And if the gradient vector is the 0 vector, then its dot product with any direction we choose is going to be equal to 0, and all of our slopes are going to be 0. And if all of our slopes are 0, that means that the tangent plane, which consists of every single tangent line at that point, smushed together, makes our tangent plane, that tangent plane is just going to be horizontal. Right? All of my tangent lines reside in a horizontal tangent plane, in the case where the gradient vector is the 0 vector. And so then you had the opportunity to practice figuring out where is the gradient vector of a given function equal to 0, and the function you were given here was 2x minus x squared minus the quantity y plus 2 squared. So you found the partial derivatives of that function with respect to x and with respect to y, set them both equal to 0, and then solved for x and y. And in the process, you found that the point at which both of them vanish at the same time, is the point 1 comma minus 2. So if this function has a local maximum point, then 1 comma minus 2 is probably its location.